Welcome. I've seen teams spend weeks debugging an issue that a 5-minute tooling setup would have caught in seconds. This lesson is about not being that team. Build, debug, and test aren't glamorous topics, but they're the foundation that makes everything else work. Compile with warnings, debug with symbols, use sanitizers to catch bugs early, and write tests that prevent regressions. These habits pay for themselves on day one. Let's get into it. Start with strong compiler warnings. -std equals C++23 sets the language standard. -wall enables most common warnings. Wextra adds additional warnings that wall misses. Wpedantic warns about non-standard extensions. Together, these flags catch suspicious code before it reaches production. Unused variables, implicit conversions, missing return statements, comparison sign mismatches. Treat every new warning as a bug report until you can justify ignoring it. Most of the time, the warning is pointing at a real problem. Fix it when you see it. 2 more flags you need. -G adds debug symbols, the information that lets a debugger show you variable names, line numbers, and source code instead of raw memory addresses. -O0 disables optimization. Without optimization, the debugger can step through code line by line and inspect variables reliably. With optimization enabled, the compiler may reorder instructions, inline functions, or eliminate variables entirely. Stepping becomes unpredictable. Use -G-O0 while diagnosing logic bugs. For sanitizers, -F sanitize equals address, undefined. AddressSanitizer catches memory errors, use after free, buffer overflows, stack overflows. UndefinedBehaviorSanitizer catches signed integer overflow, null pointer dereference, and other undefined behavior. These bugs often look random without sanitizers. With sanitizers, they produce clear error messages at the exact point of failure. Here's a complete command line workflow for small projects. G++ with C++. 23 standard, all warnings, debug symbols, and both sanitizers. Compile main.cpp into build/app. Then run it. This single command gives you strong warnings to catch code issues at compile time. Debug symbols for stepping through with a debugger. Sanitizers to catch memory and undefined behavior errors at runtime. This is enough for small projects, exercises, and experiments before you introduce CMake or a larger build system. When the project grows, move these flags into a CMake configuration, but the flags themselves stay the same. Testing advice in 3 steps. First, create a minimal failing test. When you find a bug, don't fix it immediately. First, write the smallest possible test that reproduces the failure. This forces you to understand the bug precisely. Second, fix the code. With the test in place, you'll know the moment the fix works. Third, keep the test as a regression check. That test now prevents the same bug from returning. Every bug you fix is a test you didn't have. The test-first approach makes debugging faster because you have a reliable reproducer. It makes regressions cheaper because the test catches them automatically. Over time, your test suite becomes a record of every bug the project has survived. For projects beyond a single file, CMake is the standard build system. 3 commands: CMake-S.-B, build-G, Ninja-D. CMake build type equals debug. This configures the project in a build directory using the Ninja generator in debug mode. CMake --build build. This compiles everything. ctest --test dir build --output on failure. This runs all registered tests and shows output only for failures. This three-command loop, configure, build, test, is the workflow most modern C++ projects settle on. It works the same whether you have 10 files or 10,000. A debugging loop that scales to any project size. 5 steps. First, reproduce the bug reliably. If you can't reproduce it, you can't fix it with confidence. Find the input, the sequence of operations, or the timing that triggers the failure consistently. Second, build with debug info and relevant sanitizers. Debug symbols let you step through code. Sanitizers surface memory and undefined behavior errors that are invisible otherwise. Third, reduce the failing case. Strip away everything that isn't necessary to trigger the bug. The smaller the reproducer, the easier the diagnosis. Fourth, fix the code. With a minimal reproducer and full diagnostic tools, the fix is usually straightforward. Fifth, keep the reproducer as a test. That minimal case becomes a regression test that prevents the bug from returning. 3 sanitizers, each for a different class of bug. AddressSanitizer catches memory errors, use after free, heap buffer overflow, stack buffer overflow, memory leaks. It instruments memory allocations and adds red zones around buffers. UndefinedBehaviorSanitizer catches undefined behavior, signed integer overflow, null pointer dereference, misaligned access, shift by too many bits. These bugs are technically allowed to do anything. Sanitizers make them deterministic and diagnosable. Thread Sanitizer catches data races in concurrent code. 2 threads accessing the same memory without synchronization, where at least one access is a write. Important, run sanitizers in dedicated builds. Don't combine AddressSanitizer and Thread Sanitizer in one binary. They're incompatible. Create separate build configurations for each. 3 CMake presets, or build configurations, worth having. Debug, fast rebuilds, debug symbols, no heavy optimization. This is your daily development configuration. Use it for writing code, stepping through with a debugger, and running tests. Asan Ubsan, AddressSanitizer and UndefinedBehaviorSanitizer enabled. Use this configuration when you suspect memory errors or undefined behavior. Run your test suite under this configuration regularly, ideally in CI. Release. Optimized build with -02 or -03. Use this for performance testing and final builds. Don't debug logic bugs against release builds unless the bug specifically depends on optimization. Even if you don't use CMake presets literally, thinking in named configurations keeps workflow decisions consistent across your team. When you find a bug, record 4 things before you start debugging. First, the failing input. What data, arguments, or sequence of operations triggers the failure? Second, the compiler version and platform. Bugs can be compiler-specific or platform-specific. Third, the build flags used. Was it a debug build? Were sanitizers enabled? What optimization level? Fourth, the exact observed output versus the expected output. What did the program produce? What should it have produced? This information transforms debugging from guessing into engineering. It also makes bug reports useful to other team members. A bug report that says it crashed is almost worthless. A bug report with input, compiler, flags, and output is actionable. 4 small habits that compound over time. First, keep compile commands reproducible in scripts or build files. If building the project requires remembering a sequence of flags, put them in a CMake lists file or a shell script. Second, make tests easy to run locally. If running the test suite requires a special server or a manual setup step, developers won't run tests. One command, no prerequisites. Third, don't debug optimized release binaries first. Optimization changes code layout, inlines functions, and eliminates variables. Debug against a debug build unless the bug specifically requires optimization to reproduce. Fourth, prefer one reliable build loop over many ad hoc commands. Configure once, build once, test once. The same 3 commands every time. Here's the key takeaway. A 5-minute tooling setup catches bugs that teams spend weeks debugging. Warnings at compile time, debug symbols for stepping, sanitizers for memory and undefined behavior, tests for regression prevention. These aren't advanced techniques, they're the foundation. Set them up on day 1 of every project. You've now completed the modern C++ curriculum, from getting started through advanced features, concurrency, best practices, and build workflows. 22 videos covering the complete modern C++ landscape. If this series helped you, subscribe and share it with another developer who's learning C++. Thank you for watching the entire series. Now go build something. See you in the next one.